right one there. That's how important that second code is, and that the right amino acid is there. Okay, so how many tRNAs do cells have? Some of them some vary. In order to conserve space, protozoans have a smaller number of tRNAs. The reason they need a smaller number is because this thing we call wobble here. And the wobble position in a codon anti-codon reading, right? We read the codons of the mRNA goes 1, 2, 3, so this is the 3' position of the codon. But on the other hand, remember that when you do have complementary strands, they have to be anti-parallel. So if this is 5' to 3', this is 5' to 3', and we usually count this anti-codon as 1, 2, 3, and this guy is 1, 2, 3. We always count 5' to 3'. Make sense? So this is the wobble position that occurs between the third nucleotide of the codon and the first nucleotide of the anti-codon, since they're anti-parallel. And essentially, what happens in this wobble position here is, particularly in bacteria, right? If this wobble position, if this is a U in the codon there, then it will recognize not only an A, which is the complement, but also a G and an I. It's able to base pair with these in a much weaker sense, or sort of not base paired totally in there. Okay? It has a specific amount of wobble. Due to wobble, you only need 31 tRNAs, 2 for codons with all 4 nucleotides in position 3, and 3 for codons that differ in the first 2 nucleotides of a codon. So you only need 2 for codons with 4 nucleotides in position 3. Right? So in other words, if you have a codon, go back to your table, and you look at an anti-codon, remember some of them have 4 different codons that coded for the same amino acid. If you have different nucleotides in that 4th position, you only need 2 RNAs because of this wobble, right? You can recognize A as well as G, and so forth. Does that make sense? So there's the first function of wobble is you can minimize the number of tRNAs that you need in order to recognize all of the codons, because each of the codons can be recognized, or this anti-codon on the tRNA can recognize more than one codon because of that wobble. You can recognize 2 of them, right? This tRNA here that has actually this U is in this position on the tRNA, can recognize an A or a G in the anti-codon, either one. Does that make sense? Describe it again. Does anybody have a question? You ask. Now, there's another function of this that's very important in this wobble position, and that is that when you have this wobble position between the codon and the anti-codon, the interaction between that, whatever you want to call it, the third position of the codon and its anti-codon is weaker. It's weakened because, right, you have, instead of having a U with an A, which gives you 2 hydrogen bonds, you have this U with a G or an I, which only gives you 1 in there. So you can see this cartoon is meant to say, here's an AU-based pair with 2 hydrogen bonds, here's a GC with 3, and in this wobble position, it may be this UG that only has 1 hydrogen bond. So due to wobble, the complementarity, the hydrogen bonding between this third position, 1, 2, 3, or at the wobble position is weakened. Right? Why is that important? Why do you think the wobble weakening is important?
Because the tRNA has to dissociate. tRNA has to dissociate.
It has to dissociate, and by having that wobble be weaker, it's faster, right? So you have 1 less hydrogen bond. It's enough in order to keep the integrity of that code there, so that it recognizes the right RNA. But by having that wobble there, it can pop out just a little bit quicker. As he said, you have 1 less hydrogen bond, so the bonding is weakened. Thus the bonds break easier. And believe it or not, over many, many codons, that increases the rate of translation. So the second function of the wobble position is to increase the rate of translation. So The wobble position allows for many fewer tRNAs to recognize the different codons, all 61 of the codons, and it also accelerates protein synthesis slightly. Questions? Okay. Now, what about formation of peptide bonds and protein synthesis? Protein synthesis is carried out by an enzyme that's called peptidyltransferase. And you can see, we'll see again when we look at protein synthesis on Wednesday, the shape of these tRNA molecules. In fact, these tRNA molecules are identical. The crystal structures, as I said, you can lay them out in front of you and they would look like the same molecule. The difference in the variable region. So it might differ here. This is exactly the same. That's extremely important because what that means is when these tRNAs get into the ribosome, into the two sites of the ribosome where the peptide bond is formed, the A site and P site, they're lined up exactly so that the amino acid that's attached to this guy in the amino acyl site is right there, very close to the peptide, is in the tRNA in the peptidyl site. You see what I'm saying? So this guy is right, this cartoon doesn't show this much, but this guy is right where it has to be to form that peptide bond between this amino nitrogen and the carboxyl group of the peptide. It's right there. If they were different shapes, which this sort of implies, but I don't know why they do that at a different level, but you know, if this was a bigger tRNA, if they weren't the same shape, so this was way up here, then the formation of this bond would be harder than if it was down perfectly lined up. So the structure is very, very important. The bond is formed by an enzyme that's called peptidyltransferase. And peptidyltransferase forms the peptide bond between the carboxy terminal of one amino acid here, and the amino group, the amino nitrogen of the next amino acid there. So it forms that peptide bond in there. Who knows about peptidyltransferase? What is peptidyltransferase? I told you it was an enzyme that does this, but there's no anything special about it. Well, it's part of it's in the ribosome, right? It's in the large subunit of the ribosome, I'll tell you that much. The interesting thing is if you have a ribosome and you're doing protein synthesis, right, and experimentally you're adding this amino acid to the growing chain there, you take that ribosome and treat it with protease, and it still works. Protein synthesis still works. What does that suggest? You treat it with a protease. What's a protease do? An ACE, it's an enzyme, and a protease does what? Chews up proteins, right? So if you take a protease and you put it into a protein, make sure don't take those proteins and at least break it up. Proteases are different. They have different specificity, but they'll break up a protein. So that's pretty deadly. But in this case here, if you put that protease in there, there's no problem. What does that suggest? It suggests that the enzyme peptidyltransferase is not a protein. And in fact, it's not. This is nature's first. This is the one that we know. I mean, we think that we invented these things. Long before that, nature invented a ribozyme. So the peptidyltransferase activity lies within the large, or the RNA in the large subunit. And the RNA in the large subunit, the large ribosomal subunit, is in eukaryotic cells, it's a 28S RNA, 23S in prokaryotes. But that RNA molecule has the enzymatic activity. So peptidyltransferase is a ribozyme that makes the peptide bonds between two amino acids. Yes? The last thing I want to say is that this is a picture that shows you where proteins are being made in a eukaryotic cell. And probably not so important for what we'll talk about, this certainly will be in cell biology. And that is if you look at ribosomes in cells, they occur in two different portions. One is that there are ribosomes like this that are found free in the cytosol of the cell. So this is the cytoplasm. And there are other groups of ribosomes, and these arrows here, that are attached very tightly to a set of membranes within the cell. And these membranes in the cell are the endoplasmic reticulum. So protein ribosomes that are making proteins can either be free in the cytosol of the cell or attached to the membrane, in endoplasmic reticulum of the cell. What's the difference between those two sets of ribosomes? Some of you know that. What's the difference? Why are the two? Is that meaningful, or is the cell just so jam-packed with ribosomes that they just appear to be everywhere? Do we have any idea? Let me give you a hint. If you were to take a muscle cell, right, a skeletal muscle cell where you have contraction, actin, myosin filaments, and you looked in that cell, 95% of the ribosomes would be free, and there would be much less of this endoplasmic reticulum in the cell, and very, very few, if any, ribosomes attached to the endoplasmic reticulum. On the other hand, if you took a liver cell and you looked in there, go ahead.
Does that have to do with if this cell needs to exclude large amounts of proteins?
Secreting protein. If you take a liver cell or the pancreatic cell, the actin or pancreas, right, and you're looking at, so those cells secrete a lot. Those cells have lots of endoplasmic reticulum, lots of ribosomes attached to those membranes. And that suggests right there that in cells, the secretion requires, as you just said, attachment of ribosomes through the endoplasmic reticulum, whereas muscle cells, almost all the proteins that are made stay in the cytosol, right? The actin, myosin, building filaments, building contraction. They secrete very little. They have practically no endoplasmic reticulum and no ribosomes attached. And in fact, that's true. The cytosolic ribosomes, the ones not attached to membranes, are making proteins that are used within the cell to make cellular, for cellular proteins, whereas those that are attached to the endoplasmic reticulum are making secretory proteins. The other thing in this cartoon, and it doesn't show up quite as well, I mean, you can't tell unless you're looking, but for instance, in this region here, or this region here, or this region here, cytosolic ribosomes seem to be in clumps, somewhat in clumps like this. And that's true, because proteins are essentially synthesized on not ribosomes, but polysomes. We call these polysomes. And just like when we talked about transcription, and we talked particularly that Christmas tree, the ribosomal DNA, when it's transcribed, the transcription complex gets on to the promoter region and begins transcribing, and as soon as it clears the promoter, then another transcription unit can attach. Same way here. Protein synthesis initiates when a polysome binds to the messenger RNA in the cytosol, begins translating as soon as it passes or clears the recognition site for ribosome binding, then another ribosome can bind, and it continues on until the message is covered with ribosomes, and we have polysomes. So most of the proteins in cells are translated on polysomes. Okay? Anybody have a question about any of this? Okay, so kind of made this one short today. We have okay, so listen up now. First of all, if you made this up or you took it over at the Learning Center, we'll have those on Wednesday. There's about 5 of them that are tested here. The rest of them are here. Average was 68.